Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. We are taking a deep dive today into what is probably the most essential and scoring part of Unit 9, ray optics and optical instruments. We'll be covering the principles of refraction at spherical surfaces and by lenses, and we promise a very simple, exam-safe explanation that will clear all your doubts. Okay, so let's start with a simple everyday puzzle. You probably wear spectacles, or at least you're constantly using your phone camera. Have you ever wondered how that thin piece of curved glass or plastic instantly bends light to focus it, to give you that sharp, perfect image? But a flat window pane, which is also glass, just lets light pass straight through.
That is true, actually. It's quite strange. A regular glass sheet, it has zero optical power, but my power glasses, they make the image so clear, it almost feels like magic how the curvature does that.
Exactly. And here's where it gets really interesting, especially with these counterintuitive examples. Think about someone suffering from severe nearsightedness or myopia.
Yes, I have a cousin with that.
Yeah.
She wears very thick glasses.
Right. And people with myopia, they need concave lenses to see distant objects clearly. But wait a second. A concave lens is a diverging lens. It spreads light rays out. How can a lens that spreads light actually help the eye, which needs to converge light onto the tiny retina? It seems backward, doesn't it?
It does. If the eye is already failing to converge light properly, why would you introduce something that spreads it out even more? I mean, intuitively, you would think a converging lens would be the answer.
And that's the genius of controlled refraction. You see, the diverging lens doesn't just spread light randomly, it systematically ensures that the rays from a distant object appear to be coming from a point that is much closer to the eye. By making the object effectively seem closer, it shifts the focusing action, pulling the final focal point precisely back onto the retina. This entire benefit is all thanks to controlled refraction. So what does this all boil down to? The core idea is, well, simple. When light refracts or bends at a curved boundary, the bending action happens differently at every single point on that curve.
Ah, right, because the normal line always points towards the center of curvature. So if the surface is curved, the normal must be changing direction all along the curve.
Precisely. That changing normal is the secret ingredient. This systematic, varying bend creates what we call optical power. It's the ability to converge or diverge light rays in a controlled manner without needing a reflective coating like a mirror. To help you visualize this, let's use an analogy. Imagine light rays are like cars traveling on a highway, and they are approaching a huge, curved highway ramp that leads downward into a denser medium, say a block of glass. At each point where a car enters the ramp, the road bends slightly. That's the refraction. Because the ramp is curved, cars on the outside edge and cars on the inner edge enter at slightly different angles. But the curve is designed so that all cars are systematically directed towards a central meeting point, a focus point.
So the whole point of using the curve shape is to make sure that even though light bends differently at each spot, the net result is, well, it's organized light, not just random scatter.
That's the essence of it, yes. Lenses are fundamentally solving an engineering problem. They achieve precise focusing or divergence using only the geometry of the curve and the difference in refractive index. Without this, modern tech from your phone camera to a giant telescope would be impossible. Now, let's build a strong mental image. Picture a thick magnifying glass, a biconvex lens. Parallel rays of light enter the front curve, moving from air into glass. It's a denser medium, so they bend inward toward the normal. That's the first step. Then the rays travel through the glass and hit the second curve, the exit surface. Now they are moving from glass back out to air.
Okay, so now from denser to rarer, they should bend outward, away from the normal.
Exactly. But here's the key. The shape of that second surface is engineered so that the combination of the first inward bend and the second outward bend results in a net convergence. It all comes together at a very sharp focal point on the other side. That organized double bending action is what a lens does. Now, let us see how NSERT formally defines this, starting with a single spherical surface. This is the mathematical start for all lens formulas. Could you please read the formal relation for refraction when light travels from medium 1 to medium 2?
Yes. For refraction through a spherical interface, when light travels from medium 1 with refractive index n euro to medium 2 with refractive index n euro, the relation is n by v minus n rho by u equals n minus n euro divided by r. That formula seems very dense, especially with 4 variables. And why is it structured as a difference? N euro by minus n euro by u. The mirror formula was just a simple sum.
That is an excellent point. The structure is different because it has to account for the change in medium. But this one formula, this is the absolute mathematical foundation for every lens. Let's quickly break down how we get here in a few steps. Step 1. The fundamental principle is always Snell's law, but we apply it locally to every tiny section of the curve. Step 2. As we said, the normal changes everywhere,
Right.
which means the angle of incidence changes everywhere. Step 3. This means the amount of refraction changes for every single incoming ray. So step 4 is where the magic happens. The complex geometry with object distance u, image distance v, and radius r, it all gets simplified using some clever geometry and approximations. This gives us that single, elegant formula you just read. It cleans up all the complexity.
Okay, so the geometry is the genius part, but a lens has two surfaces. So
Yeah.
how does applying that formula twice, once for R and again for R, simplify into the lens maker's equation? It feels like it should get more complicated.
That's where the thin lens approximation is so powerful. We assume the lens is thin, so the image formed by the first surface acts as a virtual object for the second surface. When you substitute these values, a lot of the terms just cancel out, leaving us with the famous lens maker's formula. So when we combine the effects of both surfaces, we get our two most important formulas. Could you remind us of the lens maker's formula first?
Yes, the lens maker's formula is 1 by F equals N by N minus 1 times 1 by R minus 1 by R. And if the surrounding medium N is air, with a refractive index of about 1, it simplifies to 1 by F equals N minus 1 times 1 by R minus 1 by R.
Excellent. That shows the connection between geometry, the R values, and the material, N. And for practical calculations, we use the thin lens equation, 1 by V minus 1 by U equals 1 by F. Finally, we measure the lens's ability with power P, which is the inverse of the focal length in meters. P equals 1 by F. The unit is dioptry. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSamiam.com. Now let's quickly use the lens maker's equation in a simple example. This will show us how shaping glass creates a specific power. Let's take a simple biconvex lens. Both surfaces curve equally. We'll use typical glass, so n equals 1.5, and we'll set the radii of curvature to 20 centimeters.
Wait, since it's a biconvex lens, the first surface curves toward the light, so RO would be positive, plus 20 centimeters. But why is the second surface R negative? I always get stuck on the sign convention.
And that is the most crucial detail for getting full marks. We follow the Cartesian sign convention. Light travels left to right. Any surface curving towards the light has a positive radius. So RO is plus 20 centimeters. The second surface, RO, it curves away from the incident light. Its center of curvature is on the left. Therefore, R must be negative, minus 20 centimeters. Always remember that for a biconvex lens. Perfect. Now let's plug these into the simplified formula. We have 1 by F equals 1.5 minus 1 times 1 by plus 20 minus 1 by minus 20. Can you simplify the terms inside the bracket?
Okay, so inside it becomes 1 by 20 plus 1 by 20. That's 2 by 20, which is 1 by 10.
Excellent. And outside the bracket, 1.5 minus 1 is 0.5. So we have 1 by F equals 0.5 times 1 by 10.
Which is 0.05. So 1 by F is 0.05.
Correct. And if we invert that, we find the focal length F is 1 divided by 0.05, which is 20 centimeters. And since the result is positive, it confirms it's a converging convex lens, just as we expected. Now, this F equals 20 centimeters is quite powerful. For power, F must be in meters, so 20 centimeters is 0.20 meters. The power P is 1 by F, so 1 divided by 0.20.
That gives a power of plus 5 dioptries. That is a very powerful lens.
It is, yes. And understanding how this power is calculated for a single lens, well, that unlocks the next level, combining multiple lenses. These exact principles are the building blocks for microscopes and telescopes, which use multiple lenses together. Okay, now, let us tackle 3 key conceptual mistakes. The silent killers that rob students of marks in exams. Misconception number 1. A lot of students think lenses work by reflection, just like mirrors. They see light focusing and assume the mechanism is the same. The correct idea is that lenses work entirely through refraction. Light has to bend at the entry surface and at the exit surface.
So a lens focuses light not by bouncing it off, but by bending it in 2 separate organized steps as it enters and leaves the glass. That's a huge difference.
It's a fundamental difference. The remember hook is, mirrors reflect, they bounce back, lenses refract, they bend through. Misconception number 2. The wrong idea is that a lens's focal length, F, is fixed only by its shape, by its R values. The correct idea is that focal length depends on both the curvature and the material's refractive index, N. If you take a glass lens and put it in water, its focal length will change completely.
Right, because the refractive index term in the formula, the N, has changed.
Exactly. So the remember hook comes from the formula itself. The lens maker's equation proves, change R or change N, you must change F. They are inseparable. And finally, misconception number 3. Students often believe that diverging or concave lenses can never be part of a real image formation system.
I struggle with this one too. If a diverging lens always spreads light, how can it ever help form a real image?
Well, the thing is, while a diverging lens alone always gives a virtual image, when it's part of a multi-lens system, like in the camera zoom lens, its output rays are then fed into the next converging lens. Diverging lenses are crucial for correcting defects or aberrations, ensuring the final real image is perfectly sharp. So the remember hook for this is, diverging lenses solo give virtual images. In complex systems, they are essential contributors to the final high-quality real image downstream. Now, for locking these concepts in, let's use some memory anchors. First, a mnemonic for the lens mechanism. Lenin S equals light enters, net separation. It reminds you light enters, refracts, then exits and refracts again, causing a net separation. For the main formula, remember the lens maker's equation with this phrase: precision engineering from simple rules. Change R or N, change F. And to get a physical feel for a converging lens, hold your hands up. Make an L shape with the thumb and index finger of each hand and face them towards each other. Now, tilt your fingers inward, curving them slightly. That physical gesture shows how the two surfaces work together to push light rays inward. And for an extreme association, remember that the correct calculation of these formulas is what allowed us to revolutionize civilization. From eyeglasses for billions to telescopes exploring the universe. A wrong formula means a world of blur. So let's quickly summarize the 3 most factual exam-safe points from this deep dive. First, refraction at a curved surface creates optical power. This is because the normal changes everywhere, allowing light to be systematically focused or spread, which is a mechanism totally distinct from mere reflection. Second, the lens maker's equation, that is 1 by f equals n minus 1 times 1 by r minus 1 by r, is your master key. It links the focal length to the material n and the curvature of its two surfaces. And third, the thin lens equation, 1 by v minus 1 by u equals 1 by f, and the power relationship, p equals 1 by f, are the essential tools you'll use to predict where images form and to design optical systems. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROF Sam.
Yes, ProfSam.com. Study hard and all the very best for your preparation.